Welcome to Lecture 3 of Introduction to Quantum Field Theory. In this lecture, I'll be discussing the first step to discussing quantum mechanics as a path integral. As a reference for this particular lecture, again, recommend the textbook Basics of Thermal Field Theory by Leine and Vuorinen, Chapter 1. From the last lecture, I would like to recall the result that we got for the quantum mechanical partition function z of t in terms of a trace of the operator e to the minus beta h hat, where h hat is just the Hamiltonian operator. Again, recall that a trace is a trace over the Hilbert space, and beta denotes the inverse temperature. We found that if we use the energy basis n for the Hilbert space, we can write down the trace simply as a sum over all the n's from 0 to infinity. And that led us to a result for the partition function. However, there's no reason for us to sort of select the energy eigenstates as the only possible basis to express the trace. We could also use the position basis to do this. So that would mean that instead of having a sum over the discrete energy levels, we would get an integral over all positions x that we have in the position basis. The next step to getting to the result we want to get at is to split the Boltzmann factor e to the minus beta h into a product of n different copies, e to the minus epsilon h hat, where epsilon is just beta divided by the number of constituents that we write down for this product. Since h hat by definition commutes with itself, there are no non-trivial commutators that we have to consider in this expression. Next, what we want to do is we want to insert unity in between these different products. Again, unity can be expressed in different ways. So for instance, in the x basis, we could express unity simply as the integral dx over ket bra x. Or we could use the momentum basis, in which we do the same thing with just the momentum basis p. You note that these different bases have different normalizations. There's a 2 pi here in the momentum basis. And as a homework, I will ask you to derive this normalization factor 1 over 2 pi for the momentum basis when using a normalization such that x and p are just e to the I px. So what we want to do is we want to insert these unities in between these factors of our product. And since we sort of want to insert, for instance, many copies of the unity with respect to position space, we need to distinguish which unity it was that we inserted. To do this, we'll just give the basis that we use different labels. So x1, x2, x3, and so on for inserting x basis number 1, 2, and so on. And the same for the p basis. So having our expression for the partition function written as integral over dx times x to the e minus epsilon hs and so on x, we insert on the right-hand side x1, the position basis 1. So we have ket x1 bra x1 here, and we have an integral over x1 for the first position basis. Then to the left-hand side of this operator, we insert a p basis, the first p basis, which we indicate by p1. So again, we have ket p1 bra p1 integrated over dp1 and the normalization of 2 pi. And then we repeat the same procedure by inserting another position basis x2, another position basis p2, and so on. If we do this, then we are putting a position basis xi to the right of every one of these factors e to the minus epsilon h hat. And we're putting a momentum basis pi to the left of every one of these factors. Since we're inserting n copies of the position basis and n copies of the momentum basis, and we have another integral that corresponds to the trace, we end up with 2n+1 integrals for the partition function z. Note that the integrand is a product of matrix elements that are of this type here. So we have a position basis to the right, exponential, momentum basis, and then a cross product where the momentum basis and the position basis have different label. Let me go one step back to show this again. So here in our example, you can see this matrix element with I is 1 appearing. So we have x1 exponential p1, p1 x2. And if we sort of went to any ith element of this insertion here, the matrix element that we would get has precisely this form here. This matrix element we can write in a form that involves just regular functions by recognizing this as just being the exponential e to the I pi xi plus 1. And if we assume the Hamiltonian to be of this canonical form that I said earlier, so the Hamiltonian just being momentum operator over 2 times the mass of the particle plus a potential operator, then we can also write this second expression here by expressing the expectation value of p to the left by acting with the Hamiltonian to the left on the position basis. So instead of having momentum operator, we just get momentum. And we'll have the potential operator v act on the right-hand side such that we just get a function v of xi rather than an operator. Of course, this only works if these two operators wouldn't commute, which they don't. So you would have to get corrections to this formula here that involve the commutators between the potential operator and the momentum operator. But because there's an epsilon in front of this Hamiltonian, and epsilon is a number that's suppressed by the number of insertions that we do, we can take this number to be very large, in which case the corrections terms that we've neglected go down as order epsilon squared. So we're going to neglect those. So ignoring these terms that sort of drop as order epsilon squared, we find that this matrix element that we have in this expression for the partition function simply is given as the exponent e to the pi xi plus 1 times another one of these matrix elements, where we can sort of pull out the factor here and get another exponent from just the xi pi matrix element. So by, again, expressing this as e to the minus I pi xi, we end up with the following form for the matrix element that is just written as e to the minus epsilon times pi squared over 2m plus v of xi minus pi xi plus 1 minus xi, where this difference comes from the fact that here the x is label I, but on the other side, the x is label I plus 1. So that accounts for this difference here. And note that I've pulled out the epsilon, so there's an epsilon now in the denominator for this expression. So we do this again for every single one of these exponents that we have in our product. So if we do that for n exponents, we get a product of the exponentials ranging from 0 to n, or an exponent of a sum ranging from 0 to n. We have our 2n plus 1 integrals. The 1 is the integral that was originally there for the trace, dx. And then we have 2n integrals that correspond to the integrals over position basis xi and momentum basis pi. The only thing that we have left is this matrix element xi with x on the very right-hand side. Note that this expression here involves one element that is x n plus 1 for the case where j is n, and that in principle is not defined. It's just that I took the value for this position basis to be equal to the original x that we have on the very left-hand side. So going back a few steps for our expression for the path integral, we have an x on the very left-hand side. I denoted this as x index n+1. So this is our expression for the partition function here. And now I can use the fact that this expression here simply is a delta function xi minus x, in which case the integral over dx here becomes trivial. We end up with now only 2n integrals for the partition function. And that concludes the lecture.